SwayamPrabha. Digital India. Educated India.
In the last few lectures, we had been discussing about kinetics of a system of particles. In this lecture, I am going to continue on that, and towards the end of this lecture, I am going to show how the equations governing the kinetics of a system of particles can be extended to that of rigid bodies. Therefore, in this lecture, we are going to start with kinetics of a system of particles and then introduce rigid body kinetics. To recapitulate what we had discussed in the last few lectures, let us consider this figure in which I have drawn n particles acted upon by forces, and we are looking at this picture in a coordinate system that is shown. We had derived the generalized Newton's second law for this system, and we have obtained this equation of motion for the motion of the center of mass of the system. What this generalized Newton's second law tells us is the rate of change of linear momentum of this system is equal to the summation of all forces acting on the system. The linear momentum of this system is mass times the velocity of the center of mass of the system. Linear momentum is of this system of particles is the product of mass and the velocity of the center of mass of the system. Normally we start discussing kinetics from a single particle, and this system shows us why we need to study the kinetics of point particles, though nothing in the real world is a point particle, but we do study point particles because ultimately for a system of particles it is the kinetics of the center of mass, which is a hypothetical point calculated from the mass distribution of this system of particles. The center of mass motion is governed by this generalized Newton's second law, which I have written here. Then we discuss the moment of linear momentum, or what is also known as angular momentum, and we had looked at two ways of calculating about 2 points. About this point O, which is the origin of our inertial frame, we had calculated the angular momentum H O as R I vector, which is the vector shown here, cross the linear momentum of that ith particle. This is the velocity, mass of the ith particle times the absolute velocity, that means the velocity that is recorded or measured by the inertial observer, gives us the linear momentum in the inertial frame. Moment of this linear momentum summed over all particles is the angular momentum calculated about the point O. Then we had also calculated the angular momentum about the point G, the center of mass. Here we took the cross product of this moment arm is rho I vector, rho I cross m I r I dot, which is the absolute linear momentum. So, mass of the ith particle times the absolute velocity measured by the inertial observer. That is how we defined angular momentum about the center of mass. And we also showed that this angular momentum about the center of mass considered with the absolute velocity of the particle, of the ith particle, is also equal to the relative angular momentum about g. And how did we define relative angular momentum? This is the same moment arm rho I is shown here in the figure cross m I rho I dot mass of the ith particle times rho I dot is the relative velocity of the ith particle with respect to the center of mass. Therefore, m I rho I dot is in some way the relative linear momentum of the particle with respect to the center of mass. Having defined that, we found that the rate of change of angular momentum about O is the moment of all forces about O, and similarly the rate of change of angular momentum about G, the center of mass, is equal to the net moment of all forces about G. Now, these two equations, the generalized Newton's second law and this angular momentum equations, this and either of these two, that defines the kinetics of this system of particles. The generalized Newton's second law is the equation about evolution of linear momentum of the center of mass, whereas the angular momentum equations tell us the evolution of angular momentum of this system of particles. The linear momentum equation, which is the generalized Newton's second law, tells us something about how this set is moving in terms of the motion of the center of mass, how that is evolving. Whereas the angular momentum equations, they tell us in some way how the orientation of this system is changing, though orientation for a system of particles is ill defined in some sense, but as we move on we will show that for a rigid body this gives us a very concrete way of knowing the orientation of the body. Therefore, these two equations, they govern the kinetics of a system of particles as we have discussed. Now, we are going to move and calculate this angular momentum about an arbitrary point. Here in the figure I have shown this arbitrary point as P, which might have motion, which has velocity, acceleration, arbitrary acceleration, and I also find out the equivalent force system at G. F is the net force acting at the center of mass and mg is the moment, because I am shifting all the forces acting on various particles to the center of mass, I will generate moments. So, mg is that equivalent moment. Therefore, this F and mg represent equivalent force system for the force distribution that was initially acting on these various particles. Let us calculate the angular momentum about this point P, arbitrary point that I have indicated. How do we calculate angular momentum about P? We take the moment arm for the ith particle, which is this vector from P to the ith particle, this is the ith particle. From P to the ith particle is rho I prime, cross this is the absolute linear momentum of the ith particle, which means mass of the ith particle times the absolute velocity or the velocity measured by the inertial observer. And that is equal to, I can write in terms of this vector rho g prime, which is a vector from P to the center of mass, plus rho I. Rho g prime plus rho I is rho I prime. Now, I open up this bracket, I simplify, I distribute this cross product over addition. This summation when I consider this first term rho g prime cross, I will get the first term as rho g prime vector cross summation of m I r I dot, and summation of m I r I dot, as you know from the definition of center of mass, is nothing but total mass times velocity of the center of mass, and that is how I get the first term. When I write the second term, I make another replacement. Rho I dot I write as velocity of the center of mass plus the relative velocity about the center of mass, and that is how I get the second term. Here I have used, as I just now told you, I have used summation of m I r I dot is equals to total mass of the system times the velocity of center of mass, and r I dot as velocity of center of mass plus relative velocity. Now, if I use these things in my expression of angular momentum about p, the first term, this does not have anything to do with this summation. Therefore, I get summation of m I rho I, which is 0. Therefore, what I am left with is only rho I cross m I rho I dot. And therefore, I can write the angular momentum about p, about an arbitrary point p, as rho g prime, which is the moment arm from p to g cross linear momentum of the whole system with the whole mass concentrated at g. So, capital G vector is the linear momentum of the center of mass, considering that the whole mass is concentrated. It is a point, as if it is a point particle with the whole mass of the system concentrated at the center of mass. Plus, this we have seen, this is Hg or even Hg rel, the relative angular momentum about the center of mass. Now, this expression of angular momentum about p is not very easily related to the moment about p, just as in the previous situations for a fixed point or the center of mass. We had this relation that angular momentum, rate of change of angular momentum about a fixed point is moment of all forces about that fixed point, or the rate of change of angular momentum about the center of mass is equal to the moment of all forces about the center of mass. Such a simple expression does not follow from here, but we can do one thing. We can relate that net moment because of all these forces acting about p. Net moment about p is nothing but this moment arm cross F, this F is the net force at g, plus net moment about g. Therefore, this equivalent force system, this is what I am using, I am shifting this to p. Therefore, this m p is nothing but the net moment acting about p, but this is not very conveniently expressed in terms of rate of change of the angular momentum about p. Okay. Now, this net force, I can use the Newton's extended Newton's second law, or what we have derived for a system of particles, is equal to the net mass times acceleration of the center of mass. That is what I have written F as, and the moment about the center of mass is equal to the rate of change of angular momentum about the center of mass. But this expression of moment about p is not very conveniently related to the rate of change of angular momentum about p. But we can do another thing. Let us look at the relative angular momentum about P. Now, how do I define the relative angular momentum about P? I consider the moment arm for the ith particle, which is the vector from P to the ith particle, cross mi rho I prime dot. This is nothing but the relative velocity of the ith particle with respect to the velocity of P. This is the relative velocity, rho I prime dot is the relative velocity of the ith particle with respect to P. Let us see where this leads us to. Here is the definition of the relative velocity. It is the absolute velocity of the ith particle minus velocity of P. R P dot is the velocity of P as measured by an inertial observer. Now, if I differentiate, take time derivative of h p rel, then I get these terms which I have obtained by substituting this here and derivating, time derivating this. Here of course, this term was also supposed to be derivated, but what we obtain if I derivate the first term h p rel dot, the first term when I differentiate rho I prime dot cross m I rho I prime dot and this term. Now, this is 0 definitely, because it is rho I prime dot cross rho I prime dot. The cross product of two identical vectors is 0. Therefore, the only term that remains is this one. This is what remains. Now, I make this step which I will explain. The first term rho I cross m I r I double dot, recall that we had written this m I r I double dot is equal to F I from the Newton's second law for the ith particle, the net force acting on the ith particle plus summation over j the internal forces, summation of internal forces from the other n minus 1 particles. So, barring the ith particle, all other particles will have some internal force contribution on the ith particle, which is indicated by F I j, and I sum over j to have the net internal force on the ith particle. Now, if I do a cross product of this with rho I prime then the first term is nothing but what we have obtained from here. On the left hand side we have exactly this, and that is equal to rho I prime cross F I plus rho I prime cross summation over j of F I j. Now, I sum this over all I particles. Now, this summation is over I. When I do that, remember this term yields terms like rho I prime cross F I j plus rho j prime cross F j I and so on. we will have terms like this, because it is now getting summed over all I and j, and we know that f j I is minus f of I j. Therefore, this term will simplify to rho I prime minus rho j prime cross f I j. Now, rho I prime minus rho j prime is nothing but the vector from the jth particle to the ith particle. Rho I prime minus rho j prime is nothing but a vector from the jth particle to the ith particle. F I j is the force vector again from the jth particle acting on the ith particle. Therefore, both are in the same direction, both are in identical direction, and cross product therefore is 0. This cross product therefore vanishes. Once I sum over all I particles, and that is how I am only left with summation over I rho I prime cross f I. So, this is the term that comes out of that. The second term is rho I prime cross m I r p double dot. And therefore, the rate of change of the relative angular momentum about p is net moment about p, because rho I prime cross f I is the net moment of all forces about p, minus this additional term. I take that additional term to the left hand side and write in this form: the rate of change of the relative angular momentum about p of the system plus rho g prime cross m r p double dot. Now, this r p double dot is nothing but the acceleration of the point p, is the acceleration of point p. Remember, p is an arbitrary point having arbitrary velocity and acceleration, and that must be equal to the net moment of all forces about p. I have removed the intervening steps and I have written the final result here. Let us now look at some special situations. What if I fix this point p? What if I fix this point p? In other words, p is a point fixed in the inertial space. Then you will find r p double dot is 0, acceleration of p will go to 0. Under this situation, this goes to 0 because it is fixed in inertial space. Therefore, this term goes to 0. I am left with this kind of an equation I have shown here. The rate of change of angular momentum about O, in this case I have fixed p, but this I derived for the fixed point O. This equation is very similar. So, it will be rate of change of angular momentum about p is equal to net moment about p, which is same as this equation. Therefore, this equation that we had derived earlier for the rate of change of angular momentum about O, a fixed point in inertial space, follows from our angular momentum equation about relative angular momentum equation about p. Therefore, this relative angular momentum about p, this equation is little more general. If I look at another situation where p is nothing but the center of mass, because p is an arbitrary point, I can take the center of mass as that point. If p is equal to g, in that case again you will notice that this vector rho g prime, that goes to 0, and therefore, we have equation something like this: the rate of change of angular momentum about g is the net moment about g, which follows again from this general equation. Therefore, our relative angular momentum equation about this arbitrary point is a more general angular momentum equation, from which at least these two definitely follow. Let us now look at under what conditions, because this equation is quite simple. The rate of change of angular momentum about some point is equal to moment about that point. This is the simplest form of angular momentum equation that you can have, and this is analogous to the extended Newton's second law or the generalized Newton's second law, which is rate of change of linear momentum is equal to force. This kind of is analogous in structure. Therefore, we would like to know under what conditions we will get from our relative angular momentum relation, how we can get this simplified equation for angular momentum. If r p double dot is equals to 0, in other words, p is a point in an inertial, is a point which can be fixed eventually, because if p has a velocity, it does not have acceleration, it might have a velocity in some inertial space. I can do a Galilean transformation and move to a frame in which p is stationary. Therefore, if p is stationary in an inertial frame, then we have this simplified equation which I have written here. H p rel dot is equals to the net moment about p for this system of particles. Next situation, when rho g prime is 0, which means p is same as the center of mass, and that is case 2 I have shown. Then also we are reduced to H p rel dot is equals to net moment about p. In that case, of course, p is equals to g, and remember that the angular momentum about g is equal to the relative angular momentum about g. Now, the third situation is interesting. When rho g prime cross r p double dot, the acceleration of p is 0, which means p is accelerating towards or away from g, but these two vectors are co-oriented. In that case also we have this reduced equation. The rate of change of angular momentum about p, relative angular momentum about p, is equal to the net moment of all forces about p. This situation arises, for example, when a disk rolls on the ground, rolls without slipping, then the point of the disk which is in contact with the ground contact point of the disk, remember, accelerates towards the center of the disk. This we had discussed in kinematics. And if the center of mass of the disk is at the geometric center of the disk, in that case this situation is satisfied, and we have this reduced angular momentum equation about that contact point. We are going to look at the decomposition of this H p rel, the relative angular momentum about p. For that, I have written rho I in terms of rho g prime plus rho I, rho g prime plus rho I as rho I prime, and rho I prime dot is rho g prime dot plus the relative velocity with respect to g. The first term that comes out by simplifying, rho g prime cross m I rho g prime dot, I have written here, and this follows from this term cross m I times rho I dot. Here, of course, in simplifying I have used once again these relations, these identities, and therefore I am led to these two terms only. These two terms survive. The first term is the angular momentum of the whole system. This is the angular momentum due to the motion of the center of mass about that point p. You see this moment arm is this vector rho g prime, and m rho g prime dot is nothing but the relative velocity of g with respect to p. Therefore, this term represents the relative angular momentum of the whole system of particles with the mass concentrated at the center of mass and that part of the angular momentum. The second term is nothing but the angular momentum due to relative motion about the center of mass, and this is same as hg rel. Okay. Therefore, we have these finally these as our governing equations for kinetics of a system of particles, most general set of equations, where the linear momentum is defined like this: the total mass of the system concentrated at the center of mass times the velocity of the center of mass. So, this is something like an hypothetical point particle with the whole mass of the system concentrated at the center of mass, and the angular momentum, relative angular momentum equation about p, where we have defined h p rel about this h p rel in terms of these this decomposition. Now, if p is a fixed point, we get back from this set, we get back our familiar equation, angular momentum equation, which is h naught dot is net moment of all forces about O. If p is same as g, then we get the familiar angular momentum equation h g dot is m g, and if p accelerates towards or away from g, then we again get back a familiar form of angular momentum equation h p rel dot is net moment about p, where the definitions of h p rel is shown here. If none of these simplifications are applicable to our system, this or this, if none of these are applicable, then we have to work with this set of equations. That completely defines our kinetics of a system of particles. Now, let us go back to the equation of motion that we had derived about g. Now, for a system of particles, we had this definition of g. We summed over the linear momenta of individual particles over all particles to find out the net linear momentum of the system, which is same as the total mass times the velocity of center of mass. When we go to rigid bodies, this summation which we have been discussing till now just gets converted to an integral. As we move to a rigid body is a collection of many particles or many small elements. We consider that this summation then can be reduced to this integral over this very small mass measure dm. Our final result remains the same, it is the total mass times the velocity of center of mass. Angular momentum about g, which was defined, this is relative angular momentum and same as the angular momentum about g as we have discussed, again gets converted to an integral rho cross rho vector dot dm. So, the measure of this integration is the small mass element. And for rigid bodies, it is very important, for rigid bodies we have been discussing this in many of the past lectures, that rho dot, this rho vector dot is nothing but omega cross rho, where now I can define omega for a rigid body. Rho dot is omega cross rho. Now, if you use this vector algebra identity, which says vector A cross B cross C is vector A dot C times B minus vector A dot B times C. If I use this identity here, so this is our A, this is B, this is C vector. If you do that, then you will arrive at this simplification using this identity. We have rho dot rho times omega minus rho dot omega times rho. Since dot product is simpler than cross product, therefore, this expression of Hg, the angular momentum about g, is very useful for calculations. I have removed the intermediate steps and written out the expression of Hg in terms of this dot products. Now, let us specialize this for planar motion. I have considered this xy frame as shown in the figure. Now, here there is a point to be noted very carefully. The center of mass of the body must lie in this xy plane. We are going to consider planar motion. The first the requirement for planar motion is all points of this rigid body definitely must move in this xy plane. But a rigid body, of course, may have some thickness or things like that. So, you can have particles which are out of this plane, but then they are moving in parallel planes. And because of this, we have the requirement that the angular velocity of this body must have a direction perpendicular to this plane. Therefore, the angular velocity omega of this rigid body must be some omega times k cap vector, which can be written in terms of this angle made by any line which is fixed on the rigid body with respect to some datum line. This is some datum line, and we can measure this angle between the datum line and the line which is fixed to the rigid body and define that as the angle or orientation of the rigid body in case of planar motion. We are going to define this vector rho in terms of only I cap and j cap, and this is true for prismatic bodies. We are going to look at this simplification first, because if the bodies are not prismatic, in case of general bodies, having planar motion and specializing the angular momentum equation to planar motion is not possible. This is what we are going to look at in a future lecture. Therefore, in this lecture, what we are going to assume is that the body is a prismatic body. That means, it is something like an extruded body. If you have this body, so this kind of a body. In this case, you can write Hg vector, you can derive this, just substitute this expression of rho and omega in here, and you will find that this dot product goes to 0, because this is k and here we do not have k. Therefore, this term goes to 0 in this particular simplifying step. We are only left with this term, which is rho x square plus rho y square times dm into theta dot k cap. And this integral we define as Ig, which is moment of inertia of this rigid body about g, and this you must have studied in mechanics. So, this is the polar moment of inertia about an axis passing through g and perpendicular to the plane. But remember, This simplification was possible only for prismatic bodies. Here I have collected all these relations. Note that in our equation of motion using the center of mass, we have these two simplified equations. The rate of change of linear momentum of center of mass is net force on the rigid body, and rate of change of angular momentum about g is equal to the net moment of all forces about g. Linear momentum is defined like this, where velocity of the center of mass is defined like this. Also remember that the location of the center of mass, which is the vector r g, is r g x I cap plus r g y j cap, and from there we have obtained this. Therefore, this requirement that g moves in this x y plane, g is moving in this plane that we are considering, x y plane, and in that case, in case of prismatic bodies, we are discussing prismatic bodies. In prismatic bodies, this mass element can be a prismatic mass element. Therefore, if you take a small mass element, it is going to be a prismatic mass element. The angular momentum about g is defined as the moment of inertia about g of this body times the omega vector, and omega vector is some theta dot k cap, and the moment of inertia about g is defined by this integral. For the Cartesian coordinate system that I have shown, we have these three scalar equations. From the vector equations, we have these three scalar equations. You should note that the linear momentum equation, which is the generalized Newton's second law, yields two scalar equations, and the angular momentum equation yields one scalar equation. Alpha is nothing but omega dot, which is theta double dot. Thus, we have three equations of motion for the body in a plane, for a prismatic body in a plane. Now, moment of inertia of bodies, this slide just shows some of the expressions of moments of inertia, which you must be familiar with. If not, you should revise these parts. Now, we look at the equations of motion of plane kinetics of a prismatic rigid body about a fixed point O. Again, this frame that I have considered, x y frame, that contains g. In other words, this r g vector can be represented as r g x I cap plus r g y j cap. The equation of motion in this case is in this form. We, as you note, that we have already derived this, that this term I g omega dot, this equation we derived in the previous case, and because that happens to be the derivative of this term, and the time derivative of this term, because this left hand side is nothing but h o dot, this is nothing but h o dot. Therefore, I have I g omega dot, and the time derivative of this gives me two terms, r g dot cross g plus r g cross g dot. Now, r g dot and g is nothing but mass times velocity of g. Now, this is also velocity of g, therefore, this is 0. I have left with only this term, and that must be equal to the net moment of all forces about O. And if you do this simplification, if you write down the scalar components, component wise if you write down, you will get these three equations. This term comes out of this cross product. Therefore, these three scalar equations give us the equations of motion for the planar motion of this prismatic rigid body. Now, we consider a general point P. Now, there can be two possible choices of P. The point P can be a point on the rigid body which is not G, or it will be a point which is on the rigid body or its extension which is fixed. For example, here I have shown in the figure, this point P is fixed, but this is a point which belongs to the rigid body. There can be examples where P can be fixed, but need not belong to the rigid body, but to an extension of that rigid body. We have these two cases, that means point P which is a point on the rigid body, not the center of mass, and a point P which belongs to the body or its extension, but which is fixed. In the first case, when it is not fixed, the point on the rigid body and it is not fixed, in that case we have these two as our equations of motion, and the definitions of G and H P rel we have defined before. H P rel simplifies to this form, and if you write down this expression, then if you use these expressions and write down this cross product in detail, you will get these terms, and from here you will get I g times omega. And if you look closely, this term is nothing but something like m times distance square, magnitude of this rho g square. This is magnitude of rho g prime square. This is magnitude of rho g prime square, this part. Therefore, mass times magnitude of rho g prime square plus I g times omega, and this is nothing but the moment of inertia about P. Therefore, H P rel in this particular situation simplifies to I P, the moment of inertia of the rigid body about P, times the omega vector. Now, when I have removed those derivation steps and I have written these equations finally in a simplified form, this is what it comes to. When I consider P as a point on the rigid body, H P rel becomes I P times omega, the moment of inertia of the rigid body about P times omega. And therefore, our equations of motion is this set. If P is a fixed point on the rigid is a point which is fixed in the inertial space, then we must be careful in drawing the free body diagram of the body, because in the free body diagram we have the force at the hinge at this fixed point that I have shown, and the generalized Newton's second law, the right hand side must include these forces. This is not to be missed. And of course, in this case the acceleration of P is 0, because it is a fixed point in inertial space. Therefore, for this system where P is a point on the rigid body and it is fixed in inertial space, our equations of motion for this rigid body boils down to these two equations. H P rel in this case is I P times omega dot, and that must be equal to the net moment of all forces, and rate of change of linear momentum of center of mass is equals to the net force. That net force must include the reaction force at the hinge. Now, we summarize what we have discussed. We started with the kinetics of a system of particles, and we looked at three special points: a point fixed in inertial space for the angular momentum equation, the center of mass, and a general point P. We wrote down the angular momentum equation for these 3 points, and we found out under what conditions we get a simplified equation of motion for the angular momentum. We then extended our formulation to the kinetics of rigid bodies, and we discussed various cases of these equations about a point fixed in inertial space, about the center of mass, and an arbitrary point which might be moving a point which belongs to the rigid body, or which might be a fixed point. The point belongs to the rigid body and it is fixed in inertial space. So, with that I will conclude this lecture.